Hello, lovely viewer. I am back again with a physics presentation that I'm giving at a conference, the Vienna Conference of Instrumentation. And I figured this is both a good way to practice and a decent way to showcase my work. And now, since last time, I've finished my PhD and I got a job as a postdoc in Germany at DESI, so the Deutsches Elektron- und Synchroton. So it's a big research center in Hamburg, basically. It also has a site in Berlin, but never mind. I'm in Hamburg. Um, So I'm giving this talk summarizing the project basically. I have 20 minutes. I know my talk is a little too long, but anyway, um, let me just go through it. It's a bit of an overview, so we won't go in too deep into anything, but you'll see. So I'll just start, I suppose. So, hello, I'm Håkan Menlev, and I'm going to talk about the Tangerine project, which is about development of high-resolution 65 nanometer silicon monolithic active pixel sensors, and I'll get to what monolithic active pixel sensors are in a few slides. So here's an outline of my talk. I'll start with an introduction to monolithic active pixel sensors and also the Tangerine project. And then I'll talk a bit about sensor design that we're doing and also lab and test beam investigations and simulation studies. And then finally, I'll give some conclusions and an outlook. And here is just a picture of our lab setup. You can see, well, this is some power supplies and our test chip and an oscilloscope. We'll get back to this as well. So monolithic active pixel sensors, or MAPs, are silicon sensors that combine the sensitive volume and the readout electronics in a single volume. So here on the right you can see a sketch of a hybrid sensor which instead has two different silicon wafers, one for readout and one sensitive volume, and they're bonded together by bump bonds, for example. Whereas in a monolithic, the readout electronics and the sensitive volume live in the same chip. And this enables a lower material budget and also a reduced complexity and a reduced production cost compared to the hybrids. And a low material budget in particular is essential for particle tracking applications, which is what we're trying to do here. Now, maps have made significant progress in recent years. So the first map sensor is used currently in the STAR experiment at Brookhaven, and they're currently used, recently installed in the ALICE experiment, and this chip is called the LP chip. I'll talk about that more on the next slide. There's also the Malta and Monopix developments that were candidates for Atlas, and there are current developments for the next ALICE tracker upgrade and also the electron-ion collider, which Thomas mentioned on Monday. So the LP chip is the current state-of-the-art maps that is installed in a collider experiment. Here's an artistic view on the right. We've seen this picture flashed a few times on this conference. So the LP uses a relatively recent development called a quadruple well technology that allows for a small collection electrode to be used, and this reduces both detector noise and power consumption. And the LP chip is made using a 180 nanometer CMOS imaging process. The nanometer here stands for the transistor size or transistor density, basically. And recently, access has been granted to a 65 nanometer CMOS imaging process, and this is envisioned to be used for the next Alice in the Tracker upgrade sensors and a few others. So this 65 nanometer process allows a higher logic density compared to previously used processes. So this means we can have smaller pixel sizes or more in-pixel functionality, so a bit cleverer pixels. It also allows for decreased power consumption. Now this process is so far unused in particle physics applications, and it's crucial to test it. This is where the Tangerine project comes in. So Tangerine, towards next generation silicon detectors. Project was started in 2021 with the aim of developing and investigating particle detection sensors in new silicon technologies. Technologies here means, for example, the 65 nanometer and small collection electrode. This presentation focuses on the work package 1 of the Tangerine project, which is about monolithic active pixel sensors. And the project encompasses all aspects of sensor developments, from electronics design and sensor design to prototype test chip characterization. So the goal is to develop a sensor with high precision and low material. So we want a spatial resolution below 3 microns if possible, a time resolution of less than 10 nanoseconds, a very low material budget, corresponding to at most like 50 micrometers of silicon, so 0.05% x over x0 if you want to think in radiation length. And we also want a per pixel charge measurement. And the primary goal of this project is to develop a new sensor for telescope use for test beams, and I'll get back to what this means in a bit. And this will demonstrate the capabilities of the 65 nanometer technology in a particle physics context, which is the important part. So, sensor design comprises both sensitive volume design and electronics design. For sensitive volume design, there are basically 3 available processes, all with a small collection electrode, and they were originally developed for a 180 nanometer CMOS imaging process. And they're called the standard process, the modified process, and the NGAP process. And you can see sketches of them here. So the standard process is Alpide-like, where we have a small collection electrode and then depletion grows from the small collection electrode. This means we're undepleted under the p-wells. Basically, charges move by drift in depleted regions and by diffusion in undepleted regions, and it's often desirable to have as big a depleted region as possible. So that's where the modified process comes in. It introduces a blanket layer of n-doped silicon, which creates a deep planar junction here, and depletion then grows from this junction. And this way we deplete under the p-wells as well. However, the field lines at the center of the p-well, so edges of the pixels, become very straight here, and we'd rather they push the charges a bit more towards the collection electrode, and this is where the n-gap process comes in. So it leaves a gap in the n layer, and this introduces a vertical junction which makes the electric field lines push the charges more towards the collection electrode. So the Tangerine current sensor architecture is described a bit here. So we have one test chip so far, which is the DSC MLR1 chip. It's shown here as a picture. It's very small. But the main purpose of it is to test a newly designed charge-sensitive amplifier circuit. So there are two amplifier variants available, and each has a Krummenasche type feedback network for continuous reset and leakage current compensation. And the chip also has a 2x2 pixel matrix with analog readout, and the pixel size there is like 16 by 16 square micrometers, so it's very small. For the next submission, the electronics and readout design is ongoing. So the final target matrix size for us is 256 by 256 pixels, which is much larger than what we have now. Each pixel, as I mentioned, is intended to have a signal amplitude readout via a time over threshold measurement. And one suggestion to achieve this is to use analog ramps, voltage ramps sent from the chip periphery. Through this, we can get a readout. This is shown as a sketch here. Here is a pulse from a pixel, and then we can, with a survey ramp, we can register the voltage levels on the survey ramp where we cross the thresholds. And then later we can send a readout ramp that gathers these voltages and matches them to a readout clock. And in this way we can get the time over threshold. I won't go into too much depth here. We have 3 electronics designers who work on this, which is very nice. Now, sensor prototype characterization. How do we do this? How do we test it? Tests are performed in labs and at test beams. So the lab tests are performed using radioactive sources and current injection pulses. And this makes it possible to look at the signal waveforms from the prototype chip, so we can read out the analog waveforms. Test beams are performed at accelerator facilities, where a beam of particles is shot through a sensor, and using then a telescope, so-called telescope made out of reference planes, we can find the particle track position at the sensor. And this can give us measurements of sensor detection efficiency and figures of merit versus different in-pixel hit positions and so on. The initial goal, as I mentioned, of the Tangerine project is to create reference planes for a new telescope for test beam usage, so to actually make a telescope rather than just testing a sensor in a telescope. So here are some lab results looking at waveforms. So we can read out the analog signal. We use an iron 55 source in the lab and also electrons from test beams. So this here is a typical analog output for a hit in the 4-pixel matrix. So this is a hit in pixel 0 in the red here, and the other pixels don't see anything. They have a bit different baselines. And in this way we can test how different bias voltages and different control currents impact the waveform parameters. And here's an example study where we studied the signal amplitude versus the bias voltage, the back bias, labeled V sub here. And this shows all 4 pixels, and each data point here is approximately 2,500 events. And one might be able to extract some little trends here, but there's not much, it's rather flat. But importantly, this is just an example, and these are the first results of a 65 nanometer map sensor at DESI, which is very cool. Now, a test beam, just briefly how a test beam works. So we have a device under test, which is placed between reference planes, and these reference planes make up a telescope. And then when we shoot particles through all this, we can use the reference plane to reconstruct the particle track. And from this, we can find the position of we can extrapolate. So we can find the position the particle was at when it hit the device under test. And then we can see how the device under test responds to a hit in that position. So this is a sketch. And here in reality, in the DESI beamline, so here we have 3 reference plane and here the other 3, and then the device under test, and also a laser alignment system. So we went to Mainz to do a test beam to the MAMI, the Mainz microtron, which is called MAMI. And the MAMI facility provides a very small beam spot, which is nice. It has a relatively low electron beam energy though, at 0.855 GeV, but a high beam current, which gives high hit rate. And we need this because our pixels are so small, but then we've also found some inefficiencies in our pixel matrix, which means we're efficient in rather a small region. So, I mean, we know that this design needs some correction to perform well, but we understand these issues well, and lessons can still be learned about the sensor operation in a test beam. So this image shows the interpolated track positions at the sensor for tracks associated to a hit in a certain pixel, and they're color-coded here, so a different pixel means a different color. And from this we can see that the 4 pixels have 4 distinct regions, which is very nice. So this shows that the current sensor already works as a pixelated sensor, even if some design updates are needed to reach high efficiency. Still cool. This leads on to the sensor simulations. So the electric fields in our sensors are highly nonlinear, so we need detailed electric field simulations, and we do that by using TCAD, technology computer-aided design, specifically Centaurus TCAD by Synopsys. And what this does is to numerically solve equations using sensor doping information. And important to note here is that the exact doping concentrations that the silicon foundry use is not available to us, but we can use generic doping profiles and then vary them to gain insight into how sensor performance is affected by different parameters. So we can always do relative measurements at least, even if we don't have proper profiles. In this way, we can test different pixel geometries and layouts in great detail. However, TCAD is very slow at simulating particle hits, and this is where we instead use the Opex squared framework to get high statistics Monte Carlo simulations. Now, the Opex squared simulations take the output of the TCAD, so the electric field and the doping concentration as input, and then use it to simulate each pixel in a pixel matrix. So in this way, we can do simulations of the full pixel hit chain, which is charge deposition, charge carrier transport, and also digitization. And together, TCAD and Opex squared are a powerful combination, so we can do detailed sensor behavior and performance simulations with high statistics, which is nice. So diving a bit more into this, TCAD, as I mentioned, is used to make detailed electric field simulations, and we use estimates of doping concentrations, not tied to a particular process, and not 65 nanometer, not 180 nanometer, importantly, but we can still do relative measurements. So we try different doping concentrations in different parts of the sensor and create electric fields for different geometries conceptually similar to the processes developed for 180 nanometer that I showed back on slide 6. We can control some aspects of the design, such as the n-gap size, and some are fixed, so we try to find the best parameters with the ones we can vary, basically. And these 3 figures show example electric field magnitudes and streamlines and depletion boundaries for the 3 main geometries, so standard process, modified process, n-gap process again. So streamlines are these black lines, so electrons will travel along the streamlines. The color corresponds to the electric field magnitude, and these white lines are the depletion boundaries. So in the standard process, you see the depletion is just around the collection electrode, basically, whereas in the modified and n-gap, they're basically fully depleted. Now, the streamlines here, I mean, in the undepleted regions, movement is primarily by diffusion, so the streamlines don't matter all that much, but when we come here, streamlines matter more in the electric field. For the modified process, you can see that, so the collection electrodes are the corners here, sorry, I should have mentioned, rather than in the center. So here in the middle, between 2 pixels, the field lines for the modified process are rather straight, but as I mentioned earlier, if we introduce the n-gap, we can push the field more towards the collection electrode. And this can be seen here in the streamlines. They actually go more towards the collection electrodes, which is nice. Now, we take these and we input them into Opex squared. So Opex squared, we can simulate energy deposits in a pixelated sensor model via Geant4, which is nice. And each pixel then contains the doping concentrations and electric fields from TCAD. And the deposited energy creates electron-hole pairs, and then we simulate the individual charge carrier propagation. And then we get the charge per incident particle event that reaches a collection electrode in every pixel. And then we can set a threshold in simulations to exclude pixels that wouldn't produce a hit with a given threshold level. And we also add some noise to the signal. We store the Monte Carlo truth and the simulated per pixel output and do some analysis. So in this way, we can simulate particle hits quite quickly and make it practical then to generate many particles hitting many different sensor positions, so we can get high statistics data, and this makes it relatively easy to test and compare different configurations and setups. The framework is also well tested and validated for known data and experiments, for example, for small collection electrode map sensors, which is basically what we use, just in a different technology. Here in a paper by Katarina Dort, this sketch just shows a particle beam from the framework, particle beam passing through a single sensor in Opex squared. Now, just to make sure we're all on the same page, here are the main three figures of merit for the simulation studies. We have efficiency, which denotes the fraction of particles that are incident on a sensor that produce a signal in the sensor. So this goes between 0 and 1, basically. So if all particles traversing a sensor produce a signal, the sensor is 100% efficient. And this is desirable to have as high as possible. It's strongly related to threshold value, and we would like it to be high across a large range of thresholds, because that would give us a more robust sensor, less sensitive to noise, basically. In Opex squared, we can find the mean efficiency across the sensor and look at efficiency versus hit position as well. We'll come to that in a bit. Now, the cluster size is the number of pixels that register a hit for a single incident particle. So it's basically a measure of charge sharing. And this will, of course, depend on where the particle hits, whether it hits between pixels or in the center. But if we do a large number of incident particles across the whole sensor, we can find a mean value. The spatial resolution we get from comparing incident particle position to reconstructed particle position. So far in the simulations, we've taken the Monte Carlo truth as the incident particle position, and then a mean position, charge-weighted mean position of a cluster of pixels as the reconstructed position. And again, doing this for many events, we can get a distribution of values, and from this extract the sensor resolution. So here's an example study comparing the three processes, standard, modified, and NGAP for a 20 by 20 square micrometer pixel size. And we can compare the performance of them. We simulate here a 5 GeV electron beam incident head-on on a single pixelated sensor, doing 500,000 events per data point. So there are error bars here, but they're very small. And by varying the hit threshold and plotting the figures of merit, we can find graphs like this one. So this one shows the mean efficiency on the y-axis and then the threshold on the x-axis. And what we can see is that as threshold increases, the standard process loses efficiency earlier than the modified and the NGAP processes. So basically, the modified process and the NGAP process have a larger operating margin than the standard process. So we can operate at high efficiency across more thresholds. The NGAP has the best efficiency of all three. Now we can also look, as I mentioned, at Inpixel efficiency maps. So this shows that for the standard, modified, and NGAP process, this is 4 pixels, so 1, 2, 3, 4, at a threshold of 200 electrons. And red here means 100% efficient, and blue then means 0% efficient. And what we can see here is that all of them are 100% efficient in the pixel centers, but at edges and corners, the standard process loses quite a lot of efficiency already at a threshold of 200 electrons. The modified process also loses some, well, also the NGAP, but the NGAP loses the least. Now we can also look at this for many threshers. So these are GIFs. You see the threshold here is counting up. The standard, modified, NGAP again. So we can just compare it for a lot of different thresholds at once. And from this, it is very clear that the standard process loses efficiency at lower thresholds than the other two. So it's starting already now, whereas the others are holding out for a bit longer. Now, if we compare the modified process to the NGAP, we can see that this sort of square shape of the efficient region lasts for longer in the NGAP process, and this means that the modified process loses efficiency at pixel corners earlier than the NGAP process does, basically. So again, NGAP process is more efficient. This is just another way of showing it. Now, we also looked at the cluster size for this. So this figure shows the mean cluster size on the y-axis and the threshold on the x-axis. And what happens here is the cluster size tends to 1 as threshold increases, and this is due to the charge being generated by traversing particle and not being enough to generate hits in more than 1 pixel eventually. But we can see that the standard process has a higher cluster size than the other two, and this is due to a larger undepleted volume at pixel edges, which means that charges at the pixel edges in the standard process move primarily by diffusion, and thus we get a larger charge cloud, which means it can spread to more pixels, and then we get a larger cluster size. Now, the resolution is very related to cluster size. This figure shows resolution in the x direction, but it would be the same in the y direction because the pixels are square and symmetric in this simulation. But since the resolution is taken, well, the reconstructed hit position is taken to be a charge-weighted mean cluster position. If we have a larger cluster, we get a better position interpolation. And what we can see then is that the standard process, so lower is better here. So the standard process has a better resolution than the other two. However, it's important to remember that the efficiency of the standard process is the lowest. So in conclusion, basically, we need to reach a balance between efficiency and resolution. We want high efficiency more than we want high resolution, really, but we really want both. So it's important to keep the threshold as low as possible, but what is possible depends heavily on electronics design and noise. Our current baseline is around 200 electrons. But the point is that if we use the method of combining TCAD simulations and Monte Carlo simulations, we can quickly produce high statistics data of different situations, which is nice. So here are some other simulation studies we performed. So we compared different doping concentrations in different parts of the sensor, compared different pixel sizes, different bias voltage configurations, and different geometries. We've also done studies of hexagonal pixels a bit. So this work has been ongoing with generic doping profiles in TCAD for a while, but it will soon be moved into Opex squared as well. So we get the high statistics Monte Carlo data. So there is some significant progress in understanding the impact of different parameters, and the conceptual design of a new sensor is being converged on, which is very nice. And this leads on to the conclusions of future work. So we've tested the first prototype chip thoroughly, both in labs and at test beams. We found some Inpixel inefficiencies, but they're well understood and will be fixed for the next submission. We're starting tests on an analog pixel test structure, which will enable us to compare sensor flavors and also see if simulation results match reality. And we're going back to Mainz in April for another test beam, and then we're doing a test beam in DESY in June, where we will test the analog pixel test structure a bit further. The simulations using generic doping profiles already give insights that we can use in sensor optimization, which is very nice. And we're currently preparing for our next sensor submission, which is called Engineering Run 1. It's on the way, and it will hold the next iteration of our chip. And there we'll test new things in electronics and also have improved electronics design and sensor design. So, in conclusion, there are exciting times ahead for this project. And that concludes my presentation. Thank you. Hooah! So that took almost 22 minutes, which means it's too long, but it's the best I can do, I'm afraid. But anyway, my presentation is tomorrow. Well, I mean, I don't know when I'll upload this, but at the time of recording, it's tomorrow. But yeah, thanks for listening anyway. If you have any questions, feel free to type them in the comments, and I'll read them and reply to them, basically. I'll also pop a link to the actual talk, I suppose, and the conference in the video description. So yeah, that's all for me for now. So I hope you have a lovely day. Bye.